Testing. Can you hear me? Scott? I'm good? All right. All right, so tonight we're going to talk a little bit about ST microcontrollers, and didn't have quite as much time as I would have liked to prepared for some demos, but I've got a little bit of stuff going on for some show and tell and hands-on stuff, at least on the screen here with the oscilloscope, which you guys might not be able to see from back there, but I'll put it up on the screen when we get to it. It sounds like a lot of you guys are interested in a little bit lower level stuff, so feel free to ask questions or ask more details, and we'll try to tailor this to what you guys want to learn, and hopefully we'll all learn a little something together tonight. As Ian said, I work for, basically, I'm one of the owners of Sternus, and Sternus is basically a consulting design firm where we built teams of consultants together to do products. And several of our past clients for both my consulting company personally and for Sternus use STM microchips as part of their designs. It's a fairly common chip these days. It's a very big family. It has a lot going with it for it. And in some cases it has a lot of resources for doing network stacked type applications like IoT as the buzzword these days, of which is what so many companies want to do, is have you connected and be able to control whatever widget you bought via your smartphone. So the ST micros allow for that quite well because they have pretty much a little bit of everything in it. So let me see here. Get the presentation back up and going here. In fact, they basically have 7 different product series, and you can choose between cost, performance, power, and just about hundreds of different combinations. Also, as far as I/O, some of the chips come in BGA with huge amounts of I/O. Some of them come in much smaller packages with less I/O depending on what you need. It's actually one of the biggest families I think I've ever seen in the microcontroller world. Of course, I used to do a lot with PIC and microcontrollers. They had a pretty wide family range. Atmel also has a decent range, but ST certainly has tried really hard to create a lot. Now, a lot of their chips claim to be pin compatible, and this was an issue that we've run into a couple of times where the hardware guys wanted to upgrade from one chip to another because of more memory or because we needed more memory, more program space, more RAM. And ST touts a lot of pin compatibility. And from a pure hardware point of view, usually it's relatively correct. But sometimes the register maps from pin family to pin family don't always match up. And of course, as you change families, the number of peripherals, like the number of I2Cs or UARTs or SPI buses, also change. And so generally, they're pretty good about pin compatibility, but it's not always as good as what they sometimes sell it to be. As well as each chip that we've had tends to have a pretty decent sized errata sheet to go with it. So these days, you buy your hardware and it's got bugs in it too, unfortunately. And usually if, I'll show you an errata sheet real quick. Usually they have either workarounds or they say if you can't live without this, then you're sort of out of luck. Is usually their typical errata sheet here. Let's see if I can find it. Let me find one real quick. So I'll just pick one. Where's one at? There we go. If I can get it to display over here. So I think since you guys are interested in a little bit lower level stuff, we'll spend a little bit more time talking about the lower level details than I normally would go through. But here's an errata sheet for the 413 family, 423 family, and they have different device markings and rev codes to keep up with the actual semiconductor itself. And then they start having these descriptions of device limitations, as they like to call them. Cortex M4 interrupted loads to stack pointer can cause erroneous behavior. Sounds very interesting, doesn't it? VDiv or V-square root instructions might not complete correctly when a very short ISR are used of the limitation here. So we won't go through all of them because there's quite a bit. But here they talk about either a workaround is available, no workaround is available, or partial workarounds. One of the chips that Matthew and I were actually using had in their earlier errata that you couldn't individually erase the flash, the internal flash by sector. It said you had to erase the whole chip. And we said, well, that's not going to work. But we were lucky that that was important enough they actually fixed it. But a lot of these, they basically give you an errata sheet and say, well, these are bugs in the hardware, but it's probably not important enough to fix. So you have it. Some of them look pretty scary a little bit there, but let's go see what they actually say about one or two of them here. So in this one, it says basically under ARM ID number 75419, an interrupt occurring during the data phase of a single word load to the stack pointer can cause erroneous behavior of the device. So basically it says if you have this sequence of instructions, it might not work right. So don't do that. It says as of today, no compiler generates these particular instructions, so don't write hand assembly code or you might run into this bug. There you have it. Yeah, a new compiler one day might start generating these instructions, and then they'll have a, oh my goodness, we need to fix the compiler moment with whoever's writing the compiler. So, even with it, these chips are complicated complicated circuitry enough that basically you get a whole list of bugs to go with each chip that you sort of have to work around or live with, or pick a different chip.
With a different set of bugs.
With a different set of bugs. Yeah, so lately, now that I understand their errata and that a couple of these issues have come back to bite me, like on the STIO bus, there's a CRC bit. And when you do a particular transaction that doesn't have a CRC in it, it always reports a failure even though it shouldn't. So it says you should ignore that error in that particular case. Such an ingenious idea from ST. So yeah, some of their workarounds are quite funny too. And for a good chuckle, you should read a couple of these because they're pretty humorous at what they consider not to be a big deal. Like in this case, don't write your code in assembly and don't use those instructions. We'll look at one more and then we'll move on from here. You guys can easily find these sheets for any particular chip. But if you do pick an ST Micro, I suggest checking out the errata before you get too far down the road to make sure there's nothing important to you or some feature that you need that doesn't work quite right, because you'll be very disappointed to get halfway through a project and then find out you should have read the errata sheet, which has happened a few times. So in this case, it says another M4 Cortex FPU it says that 14 cycles are required. And so for some reason, if you manage to have an interrupt that's less than 14 cycles, then you're probably not going to get the right answer. So the registers end up with out-of-date data. So you can disable the lazy context save of the floating point state by clearing this bit, or you can ensure that every ISR contains more than 2 instructions in addition to the exception return instruction, apparently, or your 2 workarounds. Sounds like fun. Either of those two. By the way, the lazy context saving means that basically when you go to an interrupt routine, the hardware actually saves your state for you. So I know like in the PIC days, we had to actually save our own whichever registers were important. You had to save them, go to the ISR, do your ISR, restore the registers, go back to your program, which of course all of those saves and restores take extra cycles, which makes your interrupts slower, as well as you got to figure out what you need to save and what you don't. Luckily, in the ST world, it does a pretty good job of saving the hardware state in and out of the interrupts, and it has a very complex interrupt controller to give you a lot of flexibility and power over how you handle the interrupts, which we'll talk about in a few minutes. All right, any questions about erratas and how much fun they are?
How many pages is this errata?
24 pages for this particular one. And for every different, this covers about 4 or 5 chips, and for every different ones, there's different erratas. Some of them overlap some because they use common hardware building blocks like everyone else, but some of them don't. And so, yeah, every time you change a part, you should go find the errata sheet and figure out what's wrong with the part before you start using it or prove it. And on our current project that we're doing for a client, they've changed the processor about 3 or 4 times now. So this has been a lot of extra fun of going through the errata sheet and approving whether or not we can switch to this particular part number going forward. Mostly because the firmware keeps getting bigger and bigger. So certainly something to be careful about with ST micros, and probably these days anything. I bet Atmel and Microchip, pretty much all of the chips have gotten complicated enough that there's going to be errata for almost any chip, but the STs have quite a bit because they pack a lot of stuff into each chip. So I found that to be a pretty big item to watch out for if you're designing with these chips. So some common features, the internal PLL and clock control. So in the old days, whatever clock you put into the microcontroller is what you got. These days, you can put a clock in and get 8 times, 16 times, 32 times the clock coming out. As well as these chips have internal oscillators that you can use, and you don't need any clock external. So you can run everything from an internal clock and save even more I/O pins, as long as you're willing to live with the error that goes with the internal clock. And there's ways to calibrate that out sometimes. In the third slide, of course, there's 2 internal oscillators, one for the high-speed clock, and then there's a real-time clock, and they run from different clock sources. Normally in a typical hardware design, you would run maybe anywhere between a 8 megahertz and maybe a 32 megahertz main system clock for a microcontroller typically. And then for the real-time clock, normally you use the 32 kilohertz clock crystal because you want it running really slow. And usually it's running on battery power just to keep the date and time when you turn off everything else and you put it into deep sleep. And so these chips feature that capability where you can run 2 clocks, the high-speed clock and the real-time clock separately. And the real-time clock also handles the Watchdog Timer, because if you have safety-critical devices, you don't want your processor to hang up while it's injecting people with radiation or whatnot. So you want the Watchdog Timer to bring the device back into a safe mode or recover the device. These chips also have lots of peripherals, UARTs, SPI bus, I2C. Some of them have 5, 6, 7 of them. Some of them have maybe one or two. It's mixed up all across the family depending on how many I/O or how many pins and I/Os you have and what your requirements are. And then there's a decent flexibility of routing which pins go to which of the peripherals. It's not 100% where you can just make any pin anything, but there's usually about 10 functions per pin that you can route to each pin. And luckily for us, they have a tool, which I'll show you in a little bit, that helps you figure out how to just click and route. And then that way, if you come up with a combination of peripherals or pins that are not compatible with each other, it sort of lets you know and can either help you or at least you can visualize the incompatibility and figure out how to do your pin layouts. I think for a lot of FPGAs, a lot of them these days are, some of them are 100% routable, I think, and then some have some limitations, if I recall, as well, on which pins can be which. There's also an external memory interface, which that one tends to have a lot of erratas, by the way. Luckily, I haven't used that yet. Some of the chips have DACs. Most of them have ADCs for analog, so you can read a voltage, especially battery voltage typically, or some other voltage, system voltage. And then I mentioned the Watchdog Timer and the RealTime clocks. There's also an integrated reset for making sure the voltage is within the right range. Back in the old days, we had to have like an external supervisory IC that would monitor the voltage and control the reset pin of the microcontroller. You know, lots of times the standard circuits for a microcontroller would have a simple RC type circuit that would just work pretty well at holding and at reset as the power rail came up. But as chips have gotten more complicated, you have multiple voltage systems that have voltage translators and 3.3 and 1.8 and 2.5 and all these different voltages. Some of the chips require specific sequences of the power rails, and so it's gotten more and more important to sequence the reset as well to make sure that you're sequencing your power for each of the chips and that your processor doesn't start running until the power is stable and ready to go. Otherwise, you can have unpredictable behavior. As well as brownout protection is also built in. Might as well throw it in. So the family that I'm working with mostly these days is the M4 family. It goes up to about 100 megahertz operation. Some chips go, I think, up to about 180 megahertz internal operation. Most of them are basically, the ARM core is a 3-stage pipeline with a Harvard architecture, so I'm not going to get into that too much. I guess we could have a whole nother session on processor architectures, but basically the gist of that is that the instruction data buses are separated, so it can basically be fetching and working on instruction and data separately to some degree. And with the pipeline, you actually can start part of the instructions, and the instruction may take 3 cycles, but you can go ahead and start the next instruction. So using the pipeline gives you higher performance, which is what the whole idea of RISC was, reduced instruction set architecture was built for. But to get the performance, they have to do these pipelines, but then the pipelines cause other things like at the bottom here, prefetch and branch prediction. So the problem is when you're executing ahead of yourself, you have to keep pulling instructions, but when you get to a branch, you're not sure whether you're going to branch or not branch. So why not get all of it? And that way, either way, it's loaded in. And so a lot of these had to add more complexity to do prefetching and branching to go with all the 3-stage pipelines to keep your 1-cycle instruction rate going. A lot of the M4s that are in the ST family have FPUs, floating point units, so you can offload the floating point math as well if you have, if you're doing very much floating. And they all come with what's called a 32-bit RISC instruction set. And normally, 32-bit RISC would also take up 32 bits for every instruction, at least. They came up with a thing called thumb, which is basically a way to condense some of the instructions down to even or smaller instructions, because otherwise you're taking up 4 bytes for even simple no-ops and instructions that don't need 4 bytes. And so they came up with this thing called thumb, which is basically a variation of the instruction set to make your executable size a little bit smaller. Otherwise, with 32-bit instructions, it takes up extra space. So the interesting thing is, in processor design, your old Intel compatible systems were called CISC, and they had instructions that took however long they took. And then back in the 80s, late 80s, early 90s, and maybe even a little bit before that, and some of the higher end computers, they actually came up with the RISC style instruction sets. There's also that for people that are trying to do like maybe some data intensive applications with this processor, they also threw in a couple of DSP instructions just for good measure, in case you need those. And as this says, if you were writing code on an M3, it's really easy to upgrade to M4. Now, if you're writing for M4, going back to M3 might be a little more tricky. So they made a clear path for upgrading through the families, but downgrading is probably at your own risk, so to speak. There's also a memory protection unit that can be used for either, in addition to a real-time operating system, you can create a protected memory model. So basically the operating system can run in a protected memory space and then spawn out threads or subthreads, subprocesses that could be are configured in such a way that they can't monkey with the memory of the real-time operating system, more like a Linux style system. I don't think this memory unit is quite as advanced as what you would normally see on a Linux-based system, because I think it's limited to either 5 or 6 different spaces, but it still is pretty useful, and in fact we're using that to create an exception for our stack. So there's a trick, and actually Matthew implemented it and found the references to where there's another gentleman that came up with the idea of moving the stack to the bottom of memory, so that as your stack's growing downward, eventually when you get below where memory's at, it triggers an exception. However, as we found out, there's some magical, mystical memory in this processor that doesn't trigger the exception that's right below the regular memory. Reserved. So ST told us it was reserved memory and we shouldn't use it. And we said, but we expected it to crash when it hit the reserved memory. And they said, well, no, it doesn't crash, it's just reserved. So we ended up turning on this memory protection unit to basically get it to fault when it gets below the RAM space location. So it is a useful piece of hardware that we've actually made good use of that's in these chips as well. Now, the interrupt controller. So they have like the Cadillac of interrupt controllers here compared to most processors. I mean, on PICs, usually you get 2 levels at best. Normally, you just get 1 level. In the old days, that's all you really needed. And then you handled it yourself. But here, they basically created a nested vectored interrupt controller. You got 16 priority levels with this particular chip, which is a lot. It handles up to 81 different interrupts plus the 16 generated by the core. So, I mean, that's a pretty monster interrupt controller. it basically allows you to override the higher priority states, and with this nested vectoring, you get low latency, because if you're in the middle of an interrupt, like for UART, which maybe is not too important, but your accelerometer data comes in over I2C or SPI, you can actually get an interrupt that interrupts the interrupt, so that then you can go take care of the high priority data, put it in the memory somewhere, and then go back to sending your serial port data out at a more leisurely pace. And as I mentioned before, it restores the state automatically when you exit, so you don't even have to worry about it. So to me, that's like the Cadillac of interrupt controllers. The Watchdog Timer, I put several options. I think there's 2 different variations of the Watchdog Timer, and unfortunately I don't remember the nuances between the 2. I think one is more of a windowed Watchdog Timer that sort of moves along in time. So as long as you keep kicking it within a certain amount of time, it will keep running without resetting the processor. And I think the other one's more of an absolute, more traditional watchdog, but their data sheet details a lot more description than I can provide on the Watchdog Timer. But usually these are used typically in high reliability applications, so you may or may not really need it depending on what you're doing. The real-time clock, if you're doing non-internet connected designs, like where you're not going to be connecting to the internet and you won't have access to NTP, then you might want to spend the extra few cents for the 32 kilohertz crystal so you get more accuracy. However, sometimes for cost reduction or simplicity, you can use the internal RC oscillator, but if you really expect it to be correct, like not losing more than a minute per so many hours, then you'll have to analyze what your requirements are for accuracy. Because typically, how many seconds? Was it a few seconds per minute?
It was horrible.
It's pretty bad, wasn't it?
You get what you pay for.
Yeah. You can tune each of the RC oscillators to get it a little more accurate, but because they're internal RCs, they're still going to vary with temperature, and so your mileage may vary, but it gives you a lot of options. So you can have a really inexpensive design if you can tolerate the amount of error that you get in a real-time clock, or you can spring for a 20 or 30 cent crystal and have a lot more accuracy. Any questions so far? All right, so this one is this is where the fun topics come up. So we have an internal PLL and clock control. So this is where the newest processors compared to the old slow stuff is much more interesting. So basically you can have an input clock coming in either from the internal RC oscillator or from the external oscillator, and then you can use the internal PLL to multiply it up and then divide it back down to whichever frequencies you want, within some limits, of course, which makes things a lot easier, because you can basically have a much lower external crystal, which will help you with your EMI for people that make commercial products. You're very concerned about your EMI, because if your EMI is too high, when you go to the test chamber, they tell you your EMI is too high and you're not going to be allowed to sell your product in the US unless you fix it. Which usually, if you're not careful, means that you'll be doing board spins, which are expensive and time consuming. Or you can sometimes adjust the different clocks much cheaply than a board spin. You just change the crystal to a lower crystal, change your multiplier to a higher multiplier, and you end up with the same clock frequencies inside the chip, but you have lower clock frequencies outside the chip. And also for the clock control part, basically you can turn on and off every feature of the clock that goes to every feature in this chip by turning the clock off when you do that, the power basically goes to nearly zero for that particular feature. Because when the clock's running is when the bits are fiddling and it's consuming power since it's CMOS. But you can turn off the clock, and generally it's static power for those particular features. So you only turn on the features you want to use, leave everything else off. And then you get a good power savings compared to the old days where everything was on. So to demonstrate this, this is the 16 megahertz internal clock, and then you can multiply it up with the PLL using their internal PLL to get 71 megahertz. All you gotta do is change some bits in the configuration to do that. And it seems like a minor miracle, but switch over here to a second to their tool. So ST makes this tool, which makes things a lot easier. So this is their pin design tool, and I know you can't really read it. I can't read it either. You'd have to zoom in and zoom out to really read it, even on a big screen. Because as you can see, this particular chip is a 144 pin part. So I don't know about you guys, but soldering that thing would take a little while. You do that type of soldering?
144 pin.
Is that,
You should solder
that's
his chip.
the BGA?
No, what is it, the QFM?
QFMs? Yeah.
Your chip has legs, it can be soldered.
Yeah. I've done these before, but yeah, they're pretty tedious. The more pins, the more tedious. It can be done, but it's usually not the thing you want to do very many times. It's better to pay somebody else. So let me zoom in a little bit here. So as you can see, each of these chips, you can click on it, each of the pins, and if you'd rather have a different function, you can pick a different function. And so you can go all the way around the chip and figure out what pinout you want by using this tool. And it will help you a little bit in picking a pinout that really sort of makes sense. Because like in this case, this particular one can be configured for an Ethernet function, an external memory controller, which is what it's currently configured for, an SPI, a UART, GPIO input, output, analog, event output, and another external interrupt for GPIO. So each one of these pins out of 144 has what? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 functions. So multiply that out, you got about 1,000 different combinations of pins on this thing. I mean, that's much more complicated than the good old PIC days where you had 18 pins or 20 pins or 24 pins. But we got off topic a little bit. So let's go back to clock configuration. So this is their helpful guide to how their clocks work, which is a little more complicated than you would think sometimes. So basically, you have all these different muxes that you can pick which clock goes through this mux, and it helps you a little bit as to what frequencies you end up with as you go across here. And then you have your main PLL here configured to multiply and divide out different variations of clocks. And certain things like USB has to have a 48 megahertz clock. So certain ones of these buses, each one of these has limits on what the clock range can be for each of the different buses. There's an Ethernet clock. There's memory bus clocks, DMA clocks, system timer clocks, peripheral clocks for the I2C, so you can derive your UART bit rates and your SPI bit rates. And it takes a little while to get all this configured. This tool will help you at least get a sane configuration to start with, and then you may have to tweak it a little bit.
What is the tool output? I mean, what's the, it's not just.
This tool actually generates compilable code. So you can go in under configuration and pick different libraries and different parts. So for now, I basically started with something that works with this particular demo board. So that's a good question, though.
That's what that big blue button says, generate code.
Yeah, this one
I can't
right
see
here.
that button.
Right here. Right here. Generate code. We can talk a little bit about the specifics of how this project thing works, but I wanted to touch or go through the PLL stuff a little bit more. This is interesting to everybody, right? Because, I mean, this is a modern miracle. PLL's been around since the 60s, but, you know, that gave you basically PLL digital FM receivers for your car and your house, satellite receivers. So it's been around in the RF domain for a long time, but we haven't actually had this much control of PLLs inside a microcontroller until like the last 10 years or so, especially with this many options. So basically, we could, so this section up here is for the real-time clock, which is currently just configured to use the internal clock here at 32 kilohertz. And then this is the internal RC at 16 kilohertz. And then we have an input which is using 8. So this development board comes with an 8 megahertz crystal that connects to the chip on these two pins that drive this oscillator, which then comes into this mux, goes through this PLL, and eventually generates 72 megahertz for your system clock, and then generates all of these frequencies over here on this side. Let's see. Afraid to make it too much smaller. And then you can also take the clocks and then output them to a pin, which is what I did for the oscilloscope. So right now, well, I'll get to the oscilloscope in a minute. So basically, let's say we decide we don't want to have an external clock. We're super cheap. That 5 cents is just too much because we're going to make a gazillion of these things. So we're going to go over here and say, you know what? I want the internal clock. Now it's going to tell me, oh no, that doesn't work. So I'm going to click this little button, and it's going to do a Monte Carlo simulation to figure out what does work.
Red 32.
Usually it doesn't take this long, so hopefully I didn't confuse it too much here.
Explain again what you're having it do here.
So basically, every one of these clocks over here has a constraint, like a minimum and maximum frequency. And then you have this PLL, which can be set to a multiplier and a divider. So you can get fractional clock multipliers. And so all of these different settings have to be set in a way that all of these meet their constraints, or you'll end up with undefined behavior. And so if you were manually trying to figure out the right bits for all of these in the registers, you could spend about a week probably doing what this thing normally does in about 5 seconds. Yeah. All right, let's tell it to let's turn that off. And okay.
Is this telling you the only way to win is if you don't play the game?
Buy the crystal.
That's right.
Buy the crystal. Huh. Did I set some other constraint somewhere that?
What were you clicking on?
Resolve clock issues.
Before that, what did you change?
I just changed to the HSI right here.
Oh, yeah, you
Oh, I gotta change
can't
this
run
one.
off the HSI.
There we go.
Work or not.
That will,
Disable a constraint
there we
if you
go.
don't want to use a feature.
Sorry, what was that?
You can disable some constraints in case you're not going to use that feature. In other words, not analyze if you're not going to use a certain bus or something. You turn that off.
Normally you can turn off these clocks from here out, but this block, you can't always turn this. You can use or not use some parts of this block, but if you're generating some weird frequency for one of these, then you might get, it might be sucking more power. You might end up with some undefined or oddball behavior, and you probably don't want that. So you're going to want to configure this. I think it came up with a solution. So basically now it gives us 120 megahertz Ethernet clock. It got its 48 megahertz clock for the USB. And a lot of the lower level clocks are considerably slower than they were before, if you remember what the numbers were before.
And nothing on the chip is a significant EMI issue. Is that right?
Usually inside the chip is not a problem because you got silicon sort of as a barrier to, and everything's very close together, so it's not like an antenna and emitter. But everything that comes out, every I/O line, every clock is conceivably an emitter or an antenna for either unintentional interference or picking up energy that you don't want from other devices. And so, so this gives you a lot of flexibility to run the inside of the chip a lot faster and yet be able to keep the outside frequency lower.
Does it have fairly complicated decoupling requirements? Does it have like a PLL power bus and stuff on the outside? Because usually I've seen some EMI issues on the power bus of the, a lot of these, I don't know about ST, but a lot of microcontrollers actually have separate power that has to be decoupled pretty
It
heavily.
probably does have, I'll have to look at the pinout with 144 pins. It might have separate power for the PLL clock circuitry.
That's usually where you run into EMI issues with the high speed.
Yeah, because sometimes there is a possibility for backfeeding the frequencies, the higher frequencies back out through the power that feeds this thing. Of course, if you do proper hardware design with proper bypassing, you should also be filtering a good bit of that on the power supply because power supply design is pretty darn important for most modern equipment too. Hopefully no one's skimping on the power design or the power supply capacitors and bypass caps. Hopefully not. So basically, I guess, how much more time do I have?
That's an hour if you want.
All right, well, I'll keep going. So is this enough detail on PLLs or you guys want to see any more stuff?
I would just note, this is the page in the data sheet you want to print out and have physically next to you.
When you're doing this.
To me, this is the most important page because then everything derives off this.
Yeah, because once you configure these bus clocks, all of your UARTs and everything else are going to be derived from whatever the frequency you start with is. So if you have to go back and redo this, then you're going to have to go back and redo all of those. So you want to get this design sort of basically squared away the best you can. And this tool makes it a little easier most of the time when it's not sitting there spinning, but it also shows you the internals, which makes it a lot easier to visualize how it really works. So in this case, you've got a multiplier, you got a divider. So you take your frequency, you got another divider here. So basically your 8 divided by 4, you get 2 times whatever this number is, or divided by 2 gives you the clock here. So eventually you get 120. So 2, what is that number? 120. So basically, you take 8, you divide by 4, you get 2. You multiply times 120, you get 240. You divide by 2 again, and you get 120. So it's sort of also interesting because you want to pick the numbers. I mean, there's probably multiple ways you could get the same frequencies, but some combinations of the numbers are better than others because you're multiplying up a frequency which generates error and jitter, and then you're dividing it back down, which makes it a little more stable, but also creates a little bit of jitter in it. So there's just the right trade-off, and this tool probably will help you get there a little easier than doing it by hand, per se. All right, so let's shrink this down for a minute. And of course, once you get finished with this, then you hit generate. It generates a file with all these bit settings for the registers, and then you compile it, and voila. And in that case, like, go back to the original. All right. So with this original case, it says 72 megahertz is sort of the base frequency that it's coming up with, the system clock frequency here. And so I basically routed it back out one of the pins down here. So I basically can route it back out to a pin, and then I can put an oscilloscope on it to see what the frequency looks like. So let's look at the frequency that's coming out right now real quick. So this is what the oscilloscope up here, if you guys could see it, is showing. So basically right now, you can see that we're actually getting 72 megahertz coming out of the PLL.
That's fake.
That's fake?
Is that one of those fancier ones? Is that one of those O1 oscilloscopes?
Huh?
Is that one of those O1 oscilloscopes?
No, this one's a Keysight. Well, I mean, if we have time, we can go through and actually recompile it and change it to a different frequency. But I'm going to move on a little bit. I think that's enough detail that you guys should get the picture, and that you probably should try to use that tool to help you figure out what the right frequencies are, and hopefully make life a little simpler. So let's get back to... having two screens is always fun. All right, what? All right, where did the cursor go? All right, where in the world did it go? Here it went. All right, so I went ahead and did scope plots. Let's get to, so I'll go through this part. This is more standard microcontrollers. So if you worked with microcontrollers, you're probably used to UARTs, SPIs, I2Cs. Everyone understand what all the acronyms mean and what they are? Or anyone have questions? I'll skip the stuff everybody already knows, or at least. So GPIO, so this is another place where I actually thought a lot about your EMI compliance because they like you to buy their chips and put it in millions of products. So basically the GPIOs on this system or on this chip are very programmable. you have programmable pull-ups or pull-downs. Since Scott asked me earlier sort of more detail about that, normally in the hardware design, you don't want your pins to be floating in the middle somewhere, because basically it will, in CMOS technology, which is 90% of what we use these days, when it's floating somewhere in the middle, it turns on both gates, and then you have either a short or you have power running through the gates, which is just not good. You either end up with it sucking a lot of power when it shouldn't be, or worse, it will destroy the device, because it's basically a short between the upper transistor and the bottom transistor going through the I/O gate. So you either want it to be high or low. And you can either put resistors on your circuit board and pull it high or pull it low by putting your resistors to power or ground. Or in some cases, you can basically just program the I/O, which will start up in a high impedance state. Once you have it up and running, then you can program it to be a pull-up or pull-down internal to the chip, and save yet another 1/100th of a penny for that resistor you didn't buy, as well as being able to actually configure it after the board's been designed. You also can program the output type where you have a push-pull, which again is using two transistors to either push the output high or push the output low, or what's called an open drain configuration, which requires a pull-up resistor, and then when you turn on the open drain, it pulls the signal low, which can be used for multi-drop buses and things where you might have more than one signal trying to actually talk on the same I/O line. You'd rather have it where you have a pull-up resistor and each device can pull it down, because if you have one device that's trying to push it high and one device that's trying to push it low, it's not good for the devices. Also, as we saw in the tool, there was 9 different functions for each pin. So some of those functions are called alternate functions, which is how you route the peripherals and other particular functions. So you can configure that through a set of registers to say, I want I2C1 to go to this pin and this pin, and lots of other stuff. Now, here's where we get to the EMI and more of a practical consumer-related item. If you're going to make true consumer products, you care a lot about EMI. So what they did is they give you 4 different slew rates for each I/O pin. So you can change the actual speed of the pins in the registers. So to reduce your EMI to the minimum, what you want to do is to use the slowest speed setting that your signal that you're going to be either looking at or generating will allow. And that way the transitions are going to be as slow as possible, your EMI is going to be lower, and you'll pass your tests, and you can sell 1 million widgets and be the next Bill Gates.
Or you could do like Volkswagen did. And change the software.
You can do that as long as you don't get caught. They got away with it for a while, but they got in big trouble when they got caught. So yes, you could do that, and I have run into some less than reputable FCC certifications in the past, especially when they're done in China. Sometimes you're not always sure just what was done, but that's the world we live in. Yes.
I just want to make sure I understand what you're talking about on the slew rate there. So are you saying if you change the output from high to low or low to high, that actually determines how long it will take to transition?
Yes.
Okay.
So basically, that is the definition of slew rate. Good that you asked that question.
Can you see that on the stub with that signal?
You can see it a little bit. So I went ahead and pre-captured these. We can certainly try to demo these in real time, but I was a little worried between, every time you try to do a real live demo, of course, you know what happens. So just in case, I went ahead and did the plots. But you can see here that basically the delta, this is the slowest speed setting, and the delta time is about 24 nanoseconds from low to high on this signal. This is the next speed setting up, and you get, should actually be a little faster, so that's probably not the best example. The easiest thing that I was able to see when I was experimenting it last night is when I put like 72 or 100 megahertz on this clock pin that I'm looking at with a scope. If I had it set to one of these two lower speeds, it would be flat because it basically filtered out the entire signal.
Oh, you were changing it faster than it.
Yeah,
Okay.
faster than it
If you put your
slews.
scope into FFT mode, you'll definitely see the difference.
Yeah.
You'll see all the high frequency harmonics that you create from that faster slew rate.
Yeah, that's true. I also have a spectrum analyzer, so I was hoping to have enough time to demo what the spectrum will look like if we change through the 4 slew rates, but it's probably going to take a little longer than what we have for today. So, but that's another place. So basically for one of our current clients, we started out with a little bit faster speeds on the SDIO bus, which goes to our Wi-Fi LAN chip that we're using. And so when they went to test it at the testing facility, of course, they ended up with these nice sharp harmonics out at 150, 155 megahertz. And so I went in and reduced the speeds back down to, I think I went down to medium speed about here. And those harmonics were knocked down more than enough for them to pass the actual test. So it's really quite, I mean, if you don't look at the EMI, then you would never know the difference between the different speeds. You could put it on super fast and just leave it there. But if you're going to sell a product, this is like the difference between a feature that really is worth something, to be able to just dial in how fast the signal needs to be so it's not any faster than what your requirements really need it to be, and you can easily adjust it in software. So I slowed down all of the buses to lower speeds, and then whatever EMI or over and undershoot, they addressed it with adjustment of the dampening resistors and some pi capacitor or pi filters that they had already put on the PC board but not populated. So basically the hardware design would accommodate a certain amount of EMI filtering, but to save a few pennies, if you don't need to put those capacitors and resistors on there, yet again, you know, you can save a little bit and filter it out by just changing some bits. Let's look at, so I had to change the clock back up to 72 megahertz. You can't really see a big difference here. So if I remember correctly, the different speeds are slightly different slew rates depending on your overall clock rate and the chip family. And so you have to look at the data sheet to figure out sort of what the timing and the slew rates are, what the speeds are. But normally the low speed is like a couple of megahertz. The medium speed is like maybe 10 to 15 megahertz. This speed, this high speed, is somewhere in the 20 to 50 megahertz range, and then over 50 megahertz is usually the very high, but then this is going to have the most harmonics and EMI emissions. Of course, right now, emitting a 72 megahertz clock out of this thing is probably not really good for FCC anyway, especially since I also have some nice antennas attached to it right now. So, any other questions about that? I think that's one of the key sort of a hardware-centric feature that STMicro delivers very well in their silicon for firmware developers, but you sort of have to understand the trade-offs in the hardware domain to really appreciate the PLL and appreciate this, because these are mitigation techniques for EMI that are a lot cheaper than board spins and a lot easier to reconfigure as needed. So, any questions on those? Comments?
There was a cool article, I think it was Jack Gansel, one of his customers at one point, they had a whole bunch of very old TTL circuitry, and they were replacing an old microcontroller with a new microcontroller. They weren't aware of this feature. And
The older circuits only tolerated certain rise and fall times. And so these are just too fast. So yet again, an easy fix for their problem too. Or easier. All right, so I'm not sure we'll go through as much of this, but basically the internal oscillators are actually pretty cool as long as you don't need them super accurate. But it's also a great way to be able to run a development board without having to, before you get the clock fully debugged, or if you're having clock problems or the PLL problems, then there's an alternative internal clock that you can use to configure it in a sane way and at least get your firmware loaded and running and working, and then go back and figure out the PLLs later. Because, you know, if the PLLs don't work, the firmware's not going to run if you get an invalid configuration. And it won't tell you that, it just won't run. The DMA channel. So this is another high-end feature that certainly is not available the good old PIC days or the old days. This was mostly reserved to microprocessors because they only had enough performance to take advantage of having direct memory access controllers. But this device has a huge number of DMA channels and I think 2 DMA controllers. So all of the I/O for SPI, I2C, SDIO, all of these different peripherals, you can configure them with the DMA controller, and you can either have data that runs through the system continuously if you configure it that way. So if you were collecting data from a sensor and you're streaming it to an SD card, you can configure it so the DMA engine actually does all of the streaming and the processor doesn't do anything after it configures it and tells it to start. Alternately, you know, since I/O is pretty slow, and these days firmware needs to be fast and responsive, ideally. This is another way. If you're running your microcontroller at 120 megahertz or 180 megahertz, you got a lot of speed. But then when you start talking to I2C or UARTs at even 115.2, you know, that's an infinity amount of time for each byte that you're sending out. So instead of having to manage your buffers by byte or a few byte FIFOs, you can set the DMA engine to basically, if you have like a graphics screen, like this particular development kit or discovery kit has, you can set it up to basically refresh the entire screen using the DMA engine. So you tell it where the screen starts in memory, tell it where the I/O is for getting the data out to the screen, tell it to start, and then it'll just keep reading the memory and dumping it to the display. And in the meanwhile, you can go do something else, like generate the next screen, or, you know, have a more responsive user interface. So this is another very high-end tool or very high-end feature that is available in the ST micros that normally you don't get in a lot of the lower-end micros. So I think this is worth mentioning. Now, the only downside is it's much more complex. You know, like super loop polling type programs are very easy to understand and write because you have ultimate control of the hardware and the bits. And then you step up one level to interrupt controlled or interrupt code where you have interrupts coming in. You grab data and put it in a buffer, and then your super loop comes around and gets it whenever, which gives you more responsiveness and more flexibility, but then has more complexity because now you got an ISR and you got a super loop. They got to work together. This unfortunately adds yet another level to that complexity. Now you got the ISR, the DMA engine, and your main program have to all talk and coordinate together, and you have to configure all the registers to go with all the different pieces. But for higher performance and offloading CPU task to a DMA engine, it's certainly an available feature for you if you need that power and flexibility. Now, there is one exception to this. Some of the processors come with a CCM memory, which they call the, what is it? It's basically a tightly controlled memory, like a cache memory that's tied to the processor. So you can basically put firmware or data in there and access it with zero wait state. So the processor and the memory are tightly coupled. The only thing is that particular memory is not DMA accessible because of that. So you get faster memory, but you can't put data into it without copying it from somewhere else. But for certain applications like very low latency ISRs, you could have that coupled memory running at full speed, no wait state. Or if you had a small data set, you could move the data into there, do a bunch of calculations on it. When you're done, then output the data somewhere else, and then you can DMA it at your leisure, basically. So there is a few exceptions to the DMA engine, but generally they will talk to almost anything else other than the coupled memory. And that's only available in some of their chips, not all of their chips. So yet again, depends on what you really need. The external memory interface allows you to talk to SRAM and other external chips. This development board, I believe, has a DRAM on it and our SDRAM on it, and the external memory bus is configured to talk to that. The external SDRAM actually has the video buffer for the little display on it, so that would be where you would refresh your screen to on this particular Discovery kit. It goes up to 90 megahertz and has at least a write FIFO. These days, it's not as much need for it, but every once in a while you might need something like that, because most of these processors have everything you need internal anyway. I got music.
That's your theme song.
My theme song. The DAC is not quite as common, but some of the units have one, so you could use that for what DACs are good for, generating a voltage or some type of analog signal. ADCs, so for some of these development boards, they probably use it for reading control knobs and temperature sensors. We've used it quite a bit for.
Some accelerometers still use analog output.
Yeah, and I've seen a couple of power metering chips that also generate analog voltages that are proportionate to their inputs, or frequency monitor chips. So sometimes, having an ADC is pretty handy. I guess we talked enough about the reset controller, so I'm not going to go back through that too much. These chips have both JTAG support and SWD. Most of the stuff I've been doing lately uses a little bit more of I don't know how proprietary it is, but SWD is supported pretty heavily by the ST chips, and you can use that for programming it. You can also use it for debugging, tracing. I also recently wrote an external SPI flash writer. So you write this little chunk of code that gets loaded into memory, and ST's tools will allow you to access an external SPI flash as if it is an internal flash. But you do have to customize your little program to match your system, which is a little bit of a pain, but doable. And they provide some examples of how to do that for a couple of different chips and different interfaces, which is pretty handy because we have an external S-flash that control. So like one of the uses you could have for that is you could offload the storage of all your bitmaps for a GUI into an external S-flash so that you're not eating up your internal memory space with bitmaps and things like that. Audio files, if you were doing an audio application. In our case, we're actually storing upgrade images in the other flash as well as extra firmware. And so I need to be able to program the firmware and test it, read and write it. So it's pretty, the debuggers are pretty handy. So if you get one of the Discovery kits or One of the evaluation boards, which are more fancy and a little pricier, will come with a bigger screen, the touch screen, lots of controls, even comes with Ethernet and a camera. All of these have their ST-Link programmer built into the boards. But if you need an external one, they make an external one that you can buy and just plug it into the board. So if you build your own board, you don't want to build their programmer onto your board or production board, you just have a connector. You can connect it in. Or there is a company called Seger, which makes some higher end programmers that are a little pricier. And yet again, they also come with all these lovely little connectors for plugging in to your board and programming and debugging it via that little connector. So, sure.
Discovery kit, you get that direct or from like DigiKey or somewhere? Or where
You can buy these from DigiKey. These are probably about 100-ish. The Discovery boards are usually in like the $20, $30, $40 range.
Okay.
So these are very inexpensive and actually with the demos are pretty powerful for giving a demo, or if you pick they have a wide range of them. They have different features or different screens, or some of them don't have screens. It just depends on what you sort of have an interest in. You could pick one that's sort of similar to what you want to build, and then you'd have a good starting point to start building without having to do a board layout and pay somebody to build it and all the stuff that goes with hardware. You can start with it, sort of live with the limitations, and then eventually once you know what you want, then you could commit to doing your own circuit board or design. Either if you know hardware, which I think hopefully in the future, maybe we'll have some hardware talks where we'll go through a little bit more hardware-centric design as well. But you know, it's sort of a different beast in firmware, but certainly all of these pieces are important in building something like this.
If you get on their mailing list, it seems like once or twice a year they come out with a new board and they'll offer them up for free, basically, the first 1,000 or whatever. Oh wow, it's pretty easy to get one.
Yeah, they're not really trying to make too much money on the development boards. I think they're pretty close to cost probably. I mean, their goal is to sell chips. And so the development board is just a convenient way to get people interested in wanting to use their processor for something bigger. And as a hobbyist, if you get where you're proficient at programming it, if you start doing it more professionally, then you're certainly probably going to be more apt to use their processor because you're already faster and more proficient at it. I think we covered most of the EMI implications. So of course, proper hardware design and pre-certification testing is absolutely important if you're planning on selling it and being FCC compliant. And if you're going to sell it in Europe, good luck with all of their compliance too. Actually, if you can meet FCC, generally you'll probably be okay with European compliance too. And it also depends on what device you're making, whether you're an intentional interferer or not, as to how many different FCC things you'll have to do.
Is an intentional interferer?
Yeah,
A radio transmitter.
yeah, Wi-Fi, Bluetooth, all of those are intentional transmitters. So usually, a lot of times if you buy a module, like a radio module that's already been certified, then you sort of get the benefit of their certification to a large degree, but in some cases you'll still have to retest it. In some cases you might get by with their certification if you don't modify anything. But you still, for every product you design, you still have to pass unintentional radiation tests because you're not allowed in this country to interfere with other people's electronics. So, you start messing up other people's TVs and radios, you tend to get in trouble. One of those ham radio guys will find you.
Normally it's the reverse. Ham radio is blamed for everything. And there's a book by Henry Ott, OTT, that has quite a bit on how to avoid these kind of things.
Yeah, there's some good design books out there if you're going to really get into the hardware design. Hopefully you learned something from from this talk as to some firmware things you can do to mitigate EMI above and beyond the hardware side of it. And those hardware guys are going to really love you when you tell them about that, because they probably didn't know that either. Because I think we actually got some pretty good brownie points this last time around on being able to change those values. Networking support. So as I said before, these things, the ST Micros, especially the F4 series, is a pretty high-end chip. So like with this development board, it comes with a built-in Ethernet MAC, and with a few extra components, you basically get wired Ethernet. And like in some of our designs, you can use the SDIO bus and put a Wi-Fi transceiver on it and basically get Wi-Fi capability at high performance or full speed, since the SDI bus can run at up to 50 megahertz or so. You can get plenty of performance out of it that way. So it also, we've been integrating LWIP, which is an open source stack for doing networking. It's getting pretty good. It's a good option for adding a network stack without having to start from scratch. It also has some applications like HTTP servers. So, before you start writing everything from scratch, you might want to look around on that site and see if they've already done it for you, and then you can basically utilize their code and save a lot of time. Unfortunately, in our particular project, they wanted to do everything in a framework that doesn't always work with some legacy code, so we're having to reinvent some extra stuff. Let's see, we covered most of these. The Ethernet MAC, if you're a CAN bus person, like automotive, they offer that. Seems like CAN bus seems to be headed out the door, I think, a little bit.
Still uses medical devices.
Do they? So it'll be around for a little bit longer, but I think in automobiles they go into like fiber optic or some other more advanced protocols that are a lot more impervious to EMI or electrical interference, because cars are pretty noisy. Even, I'm sure electric ones are probably pretty noisy too. So the automotive industry seems to be moving past it. SDIO, you can either use that for Wi-Fi or for an SD card. That board has the SD card, a micro SD on it. These are a few extra features you get. You get a hardware CRC. You get encryption support on some chips. So you can actually get it to offload the encryption in hardware, which is really nice. Of course, you got to write the extra software to make all that, offload it. But you get random number generator support on some. They have an ART accelerator, which is basically a 2D DMA engine for graphics, which is also another really nice feature that I haven't typically seen. Some of the chips have a TFT LCD controller built in that you can basically talk directly to a screen if you need to. Save a little bit of money from having to have an interface chip. Camera interface is on that development board, and lots of other smaller little features and gizmos for different chips, depending on what you need. If you need something more esoteric. The only downside is, like we were using random number generator support on one of the earlier chips, and then we moved to a chip that didn't have it, and then we moved back to a chip that did have it. So we're back good again. But, as you move chip, that's another problem with the pin compatibility. They're all pin compatible. They're just not feature compatible. And so, mileage, you just have to be a little careful when with their sales folks. And then as we talked a bit about the evaluation boards, ranges $14 to, I think the most expensive one on DigiKey was $500, which is still pretty inexpensive for an actual development board. I remember FPGA boards used to be like $2,500 for some of those. Or more. $5,000, depending on which ones, the higher end ones, which I thought were a little pricey. This one is the one that's up here. If you got anybody wants to come by and look at it after the fact, These are the features of this particular one. So it's 180 megahertz capable. It's got the embedded ST-Link built into this particular board, USB connectors, and it is even embed enabled for anybody that knows about embed, the online embedded development environment. So they seem to have very good software support too, which makes things so much easier. This is the features for this other development board. It's got all kinds of audio, camera, micro SD, sensors. It's got the 4-inch touch screen that looks like a cell phone, and the built-in Ethernet and the USB, higher speed USB capabilities built into that particular development board. Development environments. So I showed you the configuration code generator. How much time do I have now? I think I'm getting pretty close to the end, aren't I?
We're gonna be out of here in 30 minutes.
All right, we'll do a couple of more minutes. Is there anything in particular you guys want to see, or you want to see the code generator a little bit more?
Well, is this all like free?
Yeah.
Is their whole development environment freely available, or what? Do they have
Yes. So you could create a Eclipse-based GCC environment. Right now, all of the stuff I'm doing, there is no license fees, but they also support Kiel or Kyle, whatever. They have 2 or 3 different options that have professional licenses if you want support, and maybe a more professional compiler. But you can build an entire development system for free for all of these chips. The only thing you got to buy is the discovery board for $20 or $15, and then you're ready to go. But the downside is, Eclipse takes a little bit to set up. Setting up the ARM extensions to it take a little bit of time, and they're sort of cumbersome. And then you have to download the compilers and set everything up. So it will cost you time, but you can certainly do a system. And basically, the system I have that I'm using is a little more old school. So it runs in a, let's see if I can get it. Where'd it go? It runs in a VM under Linux, a Linux VM on this Windows laptop. And so I basically can run everything in Linux and compile all the programs. We have make files and everything. But if you're starting today or tomorrow, I would recommend using an IDE. If you have the Seger tools, you can use Ozone, which is a debugger with a really nice IDE, which I need to learn how to use a little more. I do GDB sort of old school command line. But, and so I had a little bit of trouble getting some of these demos up and running without doing it old school. But certainly there are several of these options. So the first one is free. Most of the other ones, if you do it professionally, you're going to have some fee. They have some free trial offers where you can try it out and see whether you want to pay for it.
Visual Studio Code, I've actually enjoyed too. It's really good
For this too?
for that.
Yeah.
That's cross-platform, Mac, Windows, Linux.
Yeah, so Visual Studio over the last number of years has gotten a decent amount of support for cross-platform, as well as support into other arenas outside of just the Windows C++ area. That's a good comment. Thanks.
There's also, to go along with that, there's Nano framework. It's a C# that you can write for ESP32 as well as
Yeah, I think,
one's a C#.
and even these days, I hear the word Rust come up from time to time, so there's certainly some opportunities for using that language as well. And I mentioned here TouchGFX, which is a graphics library that integrates pretty well with this, but has some pluses and minuses. And there's other options other than TouchGFX if you need graphics. Let's see, is there anything else here? right, so I think that's pretty much it for the presentation. If you want another minute or so, I'll show you one or two more things in the code generator, and I think we'll be ready to go. Unless there's any questions that I can answer while I get this back up. Any questions?
Handle the code generation. So I've used the CubeMX to kind of set up my project, and then I'll start writing some code. And I've noticed that, like, if I need to change something later, it wants to regenerate, and sometimes it'll overwrite. I know they kind of have the comments in, where it's like, put the code here, it should be overwritten, but had kind of a hard time of going back and forth between when I start coding and then making a change in, like, the CubeMX. I hadn't quite got that workflow just great.
Yeah, I've had that problem too. I used a similar environment in Microchip where they have a code generation, and most of the, when it gets confused, usually it's pretty good about popping up a merge box in those cases, which is a lot better than it just doing whatever. But if I was doing what you're saying, then I would certainly be backing it up or committing it every time before I went back and did their code generation, because it does seem to not always merge 100%.
Yeah, it works okay, but I end up having to, like, my old file, copying my code and stuff over to.
So basically, when you start this thing, you can create a project either on the processor type or the development board. You just pick from a list, and then it will give you basically sort of a starter project or starting point. And then if you want to add other or configure or add other things like a GPIO, you can click on this configuration, and then you can go through and, like we talked about pull-ups, you can change the pull-ups. You can add user labels. For some of these pins, you can change the speed. So we talked about the 4 speeds. So basically, you can go in here and click around and get a good starting point, or you can click around and let it generate code so that you'll have an example of, you know, how they expect you to code stuff. But there is a decent learning curve on the front, but they also have some good tools to sort of at least help you get started as well. So I think that pretty much covers it, unless anybody has any additional questions.
Questions? All right.
All right. Hopefully everybody learned something. That was really the point. So, and if you have any other questions, you know, hit us up on the meetup group, or, you know, let me know.
Yeah, speaking of, please start following us on Twitter if you're not already. We're trying to up that. We want to get out these announcements of our meetings now that we're live streaming. If we get any followers tonight, anybody tune in and watch the David Letterman show? I mean, the David Starling show? Somebody did. Somebody. All right. So, I know there's a lot, we used to have a lot more people that came to these meetings, but moving over here, it's getting a little harder for some people to get here, but I know a lot of them still want to make it, so let's get the word out that we are streaming them now, and at least we'll get them in that way. All right. Like I said, we got to be out here by 8:30, but feel free to mingle and chat, whatever you want to do, finish off whatever's back there.
If anybody
Anybody
wants to come up and see the demo, I can give you a more hands-on demo if you like.
Seen it,
I know, it's all old school for you.
seen it, seen that. It's just shaking. Hold him.
That might be a little bit of a problem, because that was expensive enough. I might chase you for it.
Yeah, I think they've reduced the prices a lot since you bought that one.
Probably.
They're still not cheap, but
Well, this one has the logic analyzer option too,
yeah.
a 16-channel. So this, it doesn't have the highest end bandwidth, but I got the best I could afford at the time.
They're giving out free ones right now. With this one.
I've tried that a couple of times. I still haven't got one.
Today. And I commented on the EV blog. So hopefully we'll win one. I'm afraid that installing that wireless driver in my Monte VM has completely killed all my networking. Because when I tried to come up, it was working all day, and I shut down to come here, and I powered it back up because I was going to look at some of the code, my own code, and all my networking's dead. The joys of Linux networking.
So do you do a lot of microcontroller programming?
Do some robotic stuff, so like here and there, it's kind of one of my favorite ones. But I did a motor controller for brushless DC stuff and used the ST.
ST.
So they've had some pretty good.
You worked with the SP32
I
a
did.
couple years ago
Yeah.
on one of those.
Yeah, still like that. I want to put that in a few projects. But STM has pretty good ADC and the DMA, be able to read all that, and PWM timing.
They're good chips.
Had some really nice stuff, so I got real familiar with that configuration. And yeah, it's pretty slick though.
Actually,
I
I
looked at it in a few months. It was like a totally.
I
They updated the UI
only
apparently.
use it-
There wasn't all the Facebook and the Twitter and all that stuff there either.
only use it once. Use it the main clock
Yeah, just-
setup, and then that's all I use.
Yeah, that's kind of really all I was trying to do, but I was learning, so I was like, oh, I gotta change this, and I would go back. It's kind of where I was having that trouble of like, I've already written this
actually,
code.
since you did the clock setup, this is the first time I loaded this
Oh, really?
for this presentation.
Well, he was in China bringing up a board, and that was also a microcontroller chain on the same project. That was our